In this lecture, we look at Bernoulli's equation, which is a conservation of energy idea that has to do with fluid flow. If you're looking at the pipe down below, we see that the same volume is entering on the left that leaves on the right. But there's a different velocity and a different kinetic energy for the volume that enters on the left and what exits on the right. We can see that the change in kinetic energy is equal to 1/2 times the mass of this volume, that's 1/2 times the density times this volume delta V that enters and leaves, times the difference between the two velocities, V1, the entering velocity, and V2, the exiting velocity. So you have V2 squared minus V1 squared. So you have a different kinetic energy. So where does this kinetic energy come from, this change? The change in kinetic energy is due to the work on the system. There are external forces acting on the system, and they are due to gravity and due to the pressures at the two ends of the pipe. So if we look at gravity first, gravity is a measure of this change in potential energy as it goes from the lower pipe on the left to the higher pipe on the right. And it's the mass, again, the density times delta V, times the acceleration due to gravity, little g, times the difference in the height, y2 and y1. The pressure is equal, the work due to the pressure is equal to the pressure at the entrance, P1, times delta V, minus the pressure at P2 times delta V. So the work that gravity does plus the work that pressure does is equal to the change in kinetic energy. And if we plug in all those values and rearrange them a bit, we get a symmetric equation where we have all the quantities to the left on the left and all the quantities for the right side of the pipe on the right. So we have the pressure 1 plus the 1/2 rho V1 squared plus rho times g y1 is equal to P2 plus 1/2 rho V2 squared plus rho g y2. This is Bernoulli's equation. If we had a simplified case where we let y1 equal y2, so it's just a horizontal pipe, so no change in height, then this reduces down to just this equation, which has to do with pressures and velocities. And we see that if V2 is greater than V1, that means that P2 must be less than P1. So if the velocity goes up, if it goes from left to right, then the pressure has to go down. Or conversely, if V1 is greater than V2, then P2 must be greater than P1. So if the velocity goes down, the pressure has to go up. Let's look at an example. Let's look at a squirt gun. When you squeeze the trigger, it moves a small volume of water at a velocity of about 2 centimeters per second. Here's our squirt gun, and as the plunger goes in, it squirts out some water. You can see that again. Okay, the pressure on the inside of the nozzle is about 150,000 pascals, while on the outside it's the atmospheric pressure of about 100,000 pascals. So what is the velocity of the water squirting out of the nozzle? Well, we use our equation from above for a horizontal pipe. And then we go ahead and solve for V2. And that's equal to 2 over rho, the density, times P1 minus P2, the difference in the pressure, plus 1/2 rho V1 squared, the velocity that the trigger is cylinder. And then that whole thing is square rooted. The final term is rather small because the velocity V1 is small. So that V2 is approximately equal to just the square root of 2 over the density times the difference in the pressures P1 minus P2, which is equal to 2 over 1,000 kilograms per cubic meter times 50,000 pascals, and the whole thing square rooted. And that's equal to 10 meters per second. So rather fast, considering you're moving the velocity inside the cylinder only 2 centimeters per second. Now it's going 10 meters per second, or 10,000 centimeters per second if you make a direct comparison.